Okay, hi everyone. So my name's Lewis Wooltorton, and today I'll be discussing a joint work with Peter Brown and Roger Colbeck. And the title is A Tight Analytic Bound on the Trade-off Between Device-Independent Randomness and Non-Locality. And the paper can be found on the archive with the identifier down at the bottom here. So in this presentation, I'll start by outlining device-independent randomness for you, motivate why we consider this over the device-dependent case. From there, we can move on to non-locality and randomness versus non-locality, and show how our results provide a tight bound on this question. So to motivate randomness in a cryptographic context isn't too challenging. Suppose Alice and Bob wish to share a secret key for some private communication. Well, in order to do so, they might want to use the BB84 protocol, for example, which requires both Alice and Bob to have access to their own private random numbers. And they use these random numbers to choose the measurement basis that they measure their maximally entangled state in. And according to our current understanding of physics, generation of true randomness requires quantum processes. Now, when I say a source of good random numbers or a good quantum random number generator, what properties are we looking for? Well, the first one is that from the point of view of the user, we'd like that the outputs of the measurements are uniformly distributed, so they have no predictive power over the outputs. And secondly, not only from the point of view of the user should the outputs be random or uniformly distributed, but also from the point of view of any external party, such as an eavesdropper or a general environmental system. We would like that this extra party has also no predictive power, and this gives us a notion of privacy for our quantum random numbers. So what's our goal? Well, this is to design protocols that can actually certify these two properties. And if they can't say that they're perfectly uniform and perfectly private, we'd at least like to know how close to uniform and how close to private they are. And these typically fall into two major types, depending on whether we trust the devices or whether we don't. So when I speak about our quantum random number generator, a schematic like this might come to mind. So we have a user, Alice, who's been given a device A by the manufacturer, which claims to be a quantum random number generator. So she operates in a perfectly secure lab, which is this dashed line around the outside. And in order to verify that this is a random number generator, what she does is she lifts the top of the box open and she looks inside and she looks at what the components are doing. And now what she wants to do is verify that this random number generator is indeed producing random numbers. And we can see how it works. So it just has a simple diagonally polarized photon moving into a 50-50 beam splitter, causing a detector click, which she records as an output A. Additionally, Alice has the option to change this half wave plate, which can adjust the basis that she measures in. So she might want to use the Z basis for random numbers and the X basis for phase errors, for example. Now, in order to verify that this is indeed a random number generator, Alice has to make sure that all these components are operating as they should. So the detectors are efficient. There's no errors in the beam splitter or the wave plate. And this is a perfect single photon source, which is all very difficult to implement in practice and leaves the devices vulnerable to what are called side channel attacks. So these are attacks where an eavesdropper exploits imperfection not captured in the security model and uses this to undermine the security of the devices. So what would be ideal is if Alice didn't have to look inside the box at all. She could keep the top on and just purely look at the inputs X and the outputs A and come up with a certification of randomness in this way. And it turns out this is possible. And the way she can do this is by using two devices, A and B. Again, she operates in the secure lab. And now she also uses the same mechanism to shield the devices from each other, so they can't communicate to each other. Now she supplies inputs X and Y and gets back outputs A and B. And what we can now use is a version of Bell's theorem to certify our random numbers. So restated, we can state Bell's theorem in the following way. So if to begin with, these inputs X and Y are chosen randomly. Secondly, there's this shielding, so the devices A and B can't communicate. This is known as the no signaling condition. And thirdly, if this distribution, the probability of AB given XY, violates a Bell inequality, then these outputs A and B must contain some randomness. And we can see the intuition for this because well, if these devices properly violate a Bell inequality, then there's no local hidden variable model that can reproduce the statistics. So therefore, the statistics are telling us that they're non-local. They're intrinsically not deterministic. So therefore, we can conclude that they must be quantum. Now we can move on to randomness versus non-locality and ask, well, what's the central challenge of device-independent security? And going back to our previous discussion, that's precisely saying, given an amount of Bell violation, how much randomness can we guarantee? So what we'd like is a mathematical statement that says something like, if you observe this much Bell violation, I can guarantee you at least this much randomness. This is what we call a reliable lower bound. And now I'd like to draw your attention to this figure. So if we go back to our devices here and we look at these probability distributions, P of AB given XY, we can imagine each of these as a point in some high dimensional space. And now what I've done in this figure is I've taken a 2D cross section of this high dimensional space, so like a 2D slice. And in the middle here, we can see what's called the local polytope. So any behavior or correlations that fall into this square in the middle, these admit a local hidden variable model. And we can generate this local polytope by taking the convex hull of these extremal points here. Now, there's another way that we can describe polytopes, and that's in terms of its facets. And that's precisely what our tight Bell inequalities are. So we define a tight Bell inequality as a facet of the local polytope. And we can see why this is so, because if we imagine this facet along the top here, so this is one version of the CHSH inequality, and now we look at the half space above this this inequality. You can see that any points that violate the inequality, i.e. lie in this half space, necessarily can't be local, can't admit a local hidden variable model. Therefore, they're non-local. And if we then go ahead and plot the quantum set, we see it forms this sort of circle around the local polytope. And we see that, well, we can actually achieve a violation of this Bell inequality using quantum strategies. And we can violate it maximally up to what's known as Sirelson's bound up here. And now, so this gives us a Bell inequality we can use to test for randomness. But you might notice that there's not only one type of Bell inequality we can use. We can also look at non-tight Bell inequalities. So, for example, we can look at these tangential Bell inequalities. And what I do here is I pick a point on the boundary of a quantum set, and I draw a tangent to the quantum set at that point. And we can see this actually forms a Bell inequality because, well, suppose we did an experiment and we saw a maximum saturation of this Bell inequality. Well, we know the only set of correlations that can do this is this point here. Therefore, it cannot be in the local set, and we know that this must be non-local. But it goes further because we can also sometimes show that there's a unique quantum state and measurements that can generate this point on the boundary here. So in fact, witnessing maximum saturation not only tells you that we're non-local, it actually can tell you information about the state and measurements themselves. And this is a very powerful tool. To illustrate why this could be so, like consider if we had a task in mind, such as randomness generation, and there was a particular quantum state and measurements that were ideally suited for this task. Now, if we were fortunate enough that this state and measurements generates correlations that sit on the boundary of a quantum set, and also if they have this property of self-testing, which we can design a self-test for it. What we can do is we can essentially plot these correlations on the boundary of a quantum set and come up with this tangent Bell inequality. And this now gives us a device-independent test for these quantum state and measurements for this quantum strategy. And this isn't always the case, but in some cases we can indeed find these Bell inequalities, and they can be very useful for device-independent certification of certain tasks, such as randomness generation. So what exactly is a self-test before we move on? So a self-test is this mathematical statement that says, well, given this Bell inequality, there is a unique strategy that achieves its maximum violation up to some certain symmetry constraints. Therefore, we can say that if we witness maximum violation of this Bell inequality, I can write down exactly what the quantum system must be, again, up to symmetries. So we call this property of Bell inequalities a self-testing property. And we can use this to directly infer the amount of randomness. And to see this, consider the following chain of reasoning. So if suppose we start off by witnessing maximum violation of our Bell inequality, and now according to its self-testing property, we know that we must be handling with a pure state and a particular set of measurements. And now if our state is pure, we know that there can't be any other external party. There's no eavesdropper that can be entangled with our state. So they must be in tensor product form. So they can't have any guessing power on the outcomes of our quantum measurements. So finally, what this does is we have a certified set of measurements and a certified state, so we can immediately say how random our outputs are, because we know there can't possibly be any entanglement with Eve. So what's the measure of randomness that we'd like to use for our protocols? So this will be the conditional von Neumann entropy, which is particularly useful for spot checking protocols. And this will tell us about the uncertainty in the outputs A and B, given two particular inputs, for example, x equals 0 and y equals 0. Secondly, I'd also like to, instead of talking about the CHSH inequality as a facet of the local polytope, I'll now be referring to it as a measure of non-locality. And the reason for this is, well, it turns out the CHSH inequality is the only non-trivial facet up to symmetries of the local polytope in this scenario. And moreover, we can see that if we get a violation of the CHSH inequality, the amount of violation we get gives us a notion of distance from the local set. So maximum violation is the most non-local we can be, i.e. the furthest away from the local set, and that will be up at Sirelson's bound here. So now if we put these two things together, how much randomness do we get when we're maximally non-local, i.e. achieving Sirelson's bound? Well, it turns out that Sirelson's bound is indeed a self-test, and we can see this by drawing a tangent along the top here, which touches the point only at Sirelson's bound. And what we find is that this self-tests the maximally entangled state along with some measurements. And when we look at these measurements, they're in fact not completely uncorrelated from each other. So there's actually some correlation between Alice and Bob's outputs. And this gives us about roughly 1.6 bits of randomness. And when compared to the maximum, which in a 4-outcome experiment is log 2 of 4, which is 2 bits, and we can see that, well, we have a maximum amount of non-locality, and this does not give us back maximum amount of randomness. We get something less. And that's what I'm trying to get across on this slide, is that there's this condition where if we want maximum non-locality, we necessarily can't achieve maximum randomness. And that prompts the following question. Well, can we actually improve the amount of randomness we get by using strategies that don't go for such high amounts of non-locality? And that's what randomness versus non-locality asks. So it asks the question, how much device-independent randomness can be certified by strategies with a given amount of non-locality? Initial lower bound on this question was given by Asin back in 2012. And in their work, they presented these tilted CHSH expressions. And these constructions, what they did was each expression self-tested a particular strategy. And as the non-locality of these strategies tended towards 0, so as their CHSH scores tended towards the local bound, we saw that their randomness actually tended towards the maximum of 2. And we can see this in this following plot. So on the x-axis, I've got the CHSH violation, so that's our measure of non-locality. And on the y-axis, I've got the global randomness. And for here, instead of using the von Neumann entropy, we're actually using the min entropy to stay consistent with what was used back in 2012. So what they found was for strategies achieving maximum CHSH violation, we get less than the maximum randomness. And steadily, as we relax the amount of non-locality that we go for, we can increase the amount of randomness we achieve, all the way up to asymptotically approaching 2 bits of randomness as the CHSH score approaches 2. So as the correlations approach local. Now, there's a slight issue with this if we wanted to use this experimentally, in that, well, if we want to generate close to maximum randomness, we necessarily have to use, well, according to this understanding, we might have to use correlations that lie very close to the quantum set. And this is a problem because if there's just a small amount of noise, we can see that just a bit of noise might tip these correlations from the quantum set over the boundary into the local set where no randomness can be produced. So what we've done in our work is we've added these two new curves. So to start with, we did a new analysis of the tilted CHSH inequalities back from the 2012 work, but this time with the von Neumann entropy. And we've got this this orange curve to describe that here. And what we can see is this considerable improvement where actually we're getting reasonably close to 2 bits of randomness for quite a moderate CHSH violation. And this will drastically improve the robustness, as we'll see later. Now, secondly, we can present the main result of our work, which is this blue curve going across the top here. So not only have we been able to improve upon this tilted CHSH analysis, we've actually been able to find a tight upper bound on this question. So what we find is that for CHSH violations or non-locality being arbitrarily small all the way to the large amount of about 2.6, we can achieve exactly 2 bits of randomness. So we're no longer asymptotically tending towards 2 bits. We can achieve the exact maximum all the way up to this large amount of non-locality. And what we find is only when we go for more non-locality than this threshold do we have to start sacrificing randomness. And the intuitive understanding for this is, well, in order to achieve maximum non-locality, we find that the measurements of the two devices have to be partially correlated. And whereas up here, we can achieve completely uniform randomness using completely uncorrelated measurements. So therefore, in order to get to this higher amount of non-locality, these measurements must steadily become more and more correlated up to the point where they achieve Zeroson's bound. And I can present this in a bit of a cleaner way in this plot here. And what we've done now is, again, we've plotted our blue curve, which is our main result. Again, this is the maximum achievable amount of randomness for a particular value of non-locality. And secondly, I've compared this to what's a lower bound on this question. So this orange curve here says, well, given this amount of non-locality, what's the minimum amount of randomness that can be achieved? Whereas our blue curve asks what's the maximum amount of randomness can be achieved. And I can stress that this is achievable because for each point on this curve, we have a family of quantum strategies along with their self-tests, which correspond to these tangential Bell inequalities I was talking about earlier. So now I'd like to move on to show how we can use this new understanding to improve the practical rates of our device-independent random number generators. So to start with, we did a noise analysis. So we looked at our noise model being a Werner state. So we mixed this maximally entangled state here with a uniform noise and a parameter p. And for simplicity, we assume the noiseless measurements. So how did we go about calculating the rates here? Well, the key thing to emphasize is, well, the state and measurements are not assumptions in the security proof. What we did was at a given p, we generate a set of statistics that would have been observed using this state and those measurements. And then what we do is we lower bound the randomness device independently, conditioned on observing these statistics. And we do this using the new improved numerical technique down below here, which I've cited. And this, in fact, directly lower bounds the conditional von Neumann entropy rather than the min entropy, which gives a significant boost in the rates. So what was known before we did our analysis? So we can start off by identifying this red curve, which is the CHSH curve. So this asks, if I was to use the CHSH inequality, so this facet of the local polytope that I was talking about earlier, and I was using this to generate randomness, how do the rates fare against a Werner state noise? And we can see it drops off like this. And now if we were to use the tilted CHSH using the original analysis of the min entropy, we can see that only for very, very, very small amount of noise do we actually get any increase. And it's in fact difficult to see in this figure that this actually tends towards 2 up here for zero noise. So from this, you would conclude that, well, these tilted CHSH inequalities aren't particularly useful in a experimental setup, because they're very non-robust to noise and they will never be able to really beat the CHSH in any reasonable amount of experimental regime. And now what we've done in our work is we've added these two new curves, this blue and this orange curve here. So to start with, what we did was we redid the analysis of the tilted CHSH inequality. And we did this with the von Neumann entropy instead of the min entropy using the new numerical techniques I was just discussing. And what we find is we now get this orange curve, so this considerable improvement. And now we can see this is already in the regime of consistently getting an improvement over CHSH. And in fact, it will always do just as well as CHSH, which I'll explain in a later slide. And secondly, what we've done is we've compared our optimal constructions. So these are the constructions that give the tight upper bound, and we see an additional improvement on the tilde CHSH as well. So now we can put forward this following procedure for how one might improve rates in a practical quantum random number generator that uses that's device independent. So what the experimentalist might want to do is begin by trying to estimate the noise of their maximally entangled state, so try and gauge what this parameter p might be. And following on this, they can choose their measurements from our construction that provide the optimal amount of randomness for this particular noise. And this corresponds to choosing the particular Bell inequality that self-tests these measurements and the maximally entangled state. And what they can then do is certify their randomness using this Bell inequality, and they will see that they will always do just as well, if not better, than what they would get with the CHSH inequality down here. So they will be able to sit along this blue curve here and see a improvement in their rates. And although you might think the improvement is quite small in higher noise regimes, but these device-independent experiments are typically very difficult. And they take a large number of rounds to generate any randomness expansion. So hence, any small improvement can still go a long way in getting a boost in the rates. So before I mentioned that we will always do just as well as CHSH, eventually you can see that all these curves tend towards the CHSH curve for high levels of noise. And we can understand why this is quite intuitively. So as we move to very large amount of noise, it turns out that the only Bell inequality that we can still violate are the facet Bell inequalities of the local polytope. So it seems natural that the optimal Bell inequality for large amounts of noise would indeed be these facet Bell inequalities, since they're the only ones that can get us any violation and get us any randomness at all. And because we include the CHSH in our family of optimal constructions, we can see why the optimal Bell inequality tends towards being CHSH as we move to high levels of noise. So to summarize, the take-home message here is that what we've done is we've bounded randomness versus non-locality, and we've then shown how we can use this new understanding to improve rates for practical device-independent randomness. And importantly, the practical rates that we obtained, they were all obtained using a maximally entangled state and some simple qubit measurements in the XZ plane. So this should hopefully lead to a considerable improvement in a practical experimental setup. So for future work, we'd like to consider the performance under other noise models. So for example, the detector efficiency being particularly applicable to photonic platforms. We'd like to also investigate partially entangled states and what happens when we move to more complex device-independent scenarios, so such as those with more parties and inputs and outputs. So with that, I can remind you that the paper can be found on the archive for this identifier for more information. And thank you very much for your attention. I will be very happy to receive any questions or comments and get back to you. Thank you very much.